Okay, so in last lecture we studied the heat produced in resistor is how much, that H is equal to I square RT. There are we consider one diagram. Okay, in that diagram we tells that we connect a resistor R in between 2 point A and B. Okay, and we connect a one battery. Current flow through that resistor, but we know resistor is opposed to flow of that charges. Okay, but now we have to still pass that charges through the resistor. We have to use some energy. Okay, and that extra energy that will supply us to by this battery or cell. Okay, so due to that energy, what happen, we have to move charges, means we have to do some work done there, and to that work done, that energy is used. Okay, and as the charges passes from that resistor, then that work done, what about that work done, that's the actually question. Okay, so we in last lecture we see one step in the equation that W is nothing but the H. Okay, whatever the work done we have to do throughout this resistor, okay, that directly convert into heat. Okay, whatever the extra work done we have to do to passes charges through the resistor, then what happen, that total work done is convert into the heat. Okay, now that heat is how much, that heat is equal to I square RT, where I is the current. Okay, then R is equal to resistance of that resistor, and T is equal to how much, time. T is equal to how much, time. Okay, so H is equal to I square RT, that is the total amount of heat we will get after passing current I, resistor R, and time T. Okay, if we pass for time T, resistor is R and current is I, at that time we will get that much amount of heat through that circuit. Okay, so this equation is also called as the Joule's law of heating. Okay, so Joule's law of heating tells us that if we pass electric current, okay, through any conductor material, at that time how much heat we will get, that will be proportional to, okay, this heat will be proportional to what, I square. Okay, that heat is directly proportional to I square, then this heat is also directly proportional to R, and this heat is also directly proportional to time, for which we have to pass current through the conductor. So Joule's law tells us that H is equal to I square RT. It means that whatever the heat produced through an conductor, that is directly proportional to square of electric current, then also directly proportional to resistance of that conductor material, and also heat is directly proportional to time taken, or how much time we have to pass that current through the conductor. Okay, so here these three things are important, I, R, T, on that this heat produced in an electric conductor is depend, and this law is simply called as a Joule's law. Okay, so here you have to remember these derivations. Okay, so this finally we get this equation, H is equal to I square RT. Some problems are also asked in the examination on this equation, so only you have to remember this equation. Okay, up to now we see how much heat we can produce when we pass current I, if resistor R, and for time T through a conductor, that H is equal to I square RT. That's the equation of a heat. Okay, now next topic we have to see what is unit of electric energy. Okay, in which unit we measure electric energy, that we have to see. Okay, so one equation we know, that is the electric power. Okay, power is simply what? Rate of work, how fast we can do any work, that indicate by this term electric power. Okay, and we know electric power is given by the work divided by time. Okay, work divided by time is equal to electric power, through which we get electric work is what? That is the potential difference into charge Q. Okay, V is the potential difference and Q is charge, divided by T, that is time. Okay, so electric power, work divided by time, will be equal to V into Q divided by T. Okay, but we know Q divided by T. Okay, Q by T means what? Simply charge per unit time. If a charges are flowing in unit time T, then that's we called as the electric current. So instead of this Q by T, we have to put here I, because Q by T is equal to I, that is the electric current charge per unit time. Okay, so here we know electric power is equal to P is equal to V into I. Okay, V into I. So electric power is equal to V into I. Then what is the unit of this V? That is the potential difference, that is volt. We are measure potential difference in unit volt. Okay, then second is I. I is what? Current. We measure electric current in unit ampere. Okay, so we can say that this power is equal to V into I, means their units are what? Volt and ampere. Then we can say that this P is equal to volt into ampere. Okay, now 1 volt into 1 ampere will be equal to how much? Volt means what? Joule per second. Okay, joule per coulomb. Joule per coulomb is the volt. Okay, volt is equal to joule per coulomb, and ampere is what? Charge per unit time. Okay, charge is measured in coulomb and time is measured in second. Okay, so this is the 1 coulomb per 1 second, that is the 1 ampere. Okay, and 1 volt is what? 1 joule per 1 coulomb. Okay, that is the potential difference. That simply means what? The 1 volt into 1 ampere will be equal to 1 joule by 1 coulomb into 1 coulomb by 1 second. So 1 coulomb will get cancelled over here. Okay, 1 coulomb will get cancelled. So what is remaining? That is the 1 joule divided by 1 second, and that will be the equal to unit of electric power P. Okay, that is the 1 joule per 1 second, and that's called as the watt. It is represented by letter capital W, and it called as a watt, W-A-T-T, watt. Okay, so this is the unit of electric power. Electric power measured in unit watt. Okay, actually this watt is a very small unit. Okay, in our day-to-day life, for the conventional use of electricity, it's a very small unit. Okay, so for that we have to use kilowatt. That unit we generally use in case of electricity, kilowatt. Then in kilowatt, how much unit? So in generally in our day-to-day life, we say 5 unit electricity we are use. In whole a month we use 100 units. So this unit is what? That unit concept we have to see in next part. Okay, so up to now you have to remember this: the unit of electric energy is watt. Okay, so now we have to see the what is the actually 1 unit electricity. Okay, so next topic we have to see, that is 1 unit electricity. Okay, this word generally we use for our day-to-day use of electricity, we know the unit of electricity is watt. Okay, but I already told you this watt is a very small unit for the conventional use. Then instead of watt we have to use generally kilowatt. Okay, now kilo means what? Kilo means 10 raised to 3. Try to remember that is the 1000. Okay, that is the 1000. So we have to use this kilowatt unit for the conventional use of electricity, that is the 1000 watt. Now if we use this 1 kilowatt energy for 1 hour, okay, 1 kilowatt energy for 1 hour, then we can call as a 1 kilowatt hour. Okay, 1 kilowatt energy in 1 hour, so that is the 1 kilowatt energy in 1 hour. Okay, so we know 1 kilowatt hour means how much? Simply in 1 kilowatt means 1000 watt into in 1 hour. Generally we have to use unit second for the time. Okay, and we know in 1 hour 60 minutes. Okay, and in 1 minute 60 seconds. Okay, so total 3600 seconds are there in 1 hour. Okay, so instead of this hour we have to use second. Okay, and in 1 hour we know 3600 seconds are there. Okay, so it will be equal to 3.6 into 10 raised to 6. This is watt and this is second. Watt second. 3.6 into 10 raised to 6 watt second. This watt second is nothing but the joule. Okay, so 1 kilowatt hour energy is equal to 3.6 into 10 raised to 6 joule. Okay, and this much energy is nothing but the 1 unit. Okay, if we use 1 kilowatt hour, that much energy, that is 3.6 into 10 raised to 6 joule energy, that is the 1 unit energy. Okay, so you have to remember 1 unit is equal to 3.6 into 10 raised to 6 joules. That is nothing but the 1 unit of our electric meter reading. Okay, this value is also asked in many competitive examinations. Okay, only power will change there. 10 raised to 4, 10 raised to 3, 10 raised to 7, 10 raised to 6. Okay, so you have to remember 3.6 into 10 raised to 6 joule is nothing but the 1 kilowatt hour, and 1 kilowatt hour is nothing but the 1 unit of electricity. Okay, so watt is a unit, but for conventional use we have to use kilowatt hour. Okay, kilowatt, 1 kilowatt energy we have to use in 1 hour. How much energy we use in 1 hour? So from that we get the 1 unit, and that nothing but the 3.6 into 10 raised to 6 joule. Okay. Okay, so next topic we have to see, that is heating effect of electric current. Okay, due to the electric current, different effect we have observed. Okay, in that heating effect is that. Another one is we have to see, that is the magnetic effect of electric current, that will be seen later part. But now we have to see heating effect of electric current. Due to the electric current, simply heating effect of electric current, this word indicates that simply due to the electric current, heat is a produce. Okay, in a heating effect what happens, heat is generated by a resistor in electric circuit, that is called as heating effect of electric current. If we are connect resistor, we are see in first example that we draw one diagram here. Okay, in that diagram we see that we are connected one resistor here. Okay, due to that resistor what happen, we have to pass current through that resistor, then we have to do somewhat work done. Okay, and for that work done we need some energy, and that energy is supplied by the battery. Okay, simply by using that energy, charges are passed through the resistor, and after pass through resistor, whatever the work we do to pass that charges from the resistor, what happen there, that total work done is get convert into heat. Okay, that we already see. We see there W is equal to H, that part. Okay, W is equal to H, and H is equal to I square RT, that we see in the Joule's law of heating. Okay, so simply from that we can say that if you connect a resistor in an electric circuit, then due to that resistor, what happen, heat is produced in an electric circuit. That's simply called as a heating effect of electric current. Okay, now this heating effect of electric current we see in various home appliances. Okay, electric cooker, electric bulb. Okay, these are the some common example of this heating effect of electric current. Also electric water boiler. Okay, that is also one example of heating effect of electric current that we use in our day-to-day life. Okay, so in that such a home appliances, some substances are used which having very high electric resistance. Okay, and we know we have to pass the current through that resistor substances, we have to do some work done. Okay, and finally if charges are passed through that resistors, then whatever work we have to do, that get converts into heat, that we see in the Joule's law of heating. Okay, so here such substances are used which having very high resistance in the electric circuits. Okay, due to that what happens, simply we have to do some extra work to pass that charges, and that extra work will get convert into the heat. Okay, so that heat we have to use for our various applications, whether we have to use as a bulb, okay, or whether we have to cooking, or whether we have to boiling water. Okay, that depend on the basis on the purpose of that particular home appliance. Okay, so only we have to remember here, heating effect of electric current means what, when we are connect resistors in an electric circuit, then due to the resistor what happen, heat is produced in that electric circuit, that is nothing but the heating effect of electric current. Okay, then in such substances, in such a electric connection, substances are used which having very high resistance. Okay, due to that what happen, we are get high heat. Actually coils of such substances are used there. Okay, so due to that we get very high heat. The example is nichrome. Okay, this nichrome is used in electric cooker. So coils of nichromes are used there. Okay, large number of coils are present there. So what happen, large resistance is present there, and we know if resistance is present, then we have to do some extra work, and that extra work get converted into the heat. Okay, so large coils are present there, due to that large heat is produced. Okay, whatever the work we have to do there to pass charges through that coils, that get converted into the heat. Okay, so as a number of coils were increased, simply generation of heat will be large, and also melting point of this nichrome is very high, that is 1400 degrees Celsius. So it not easily melts, so it will give us very high heat but not melts. That is the one important, we can say, that use of this nichrome to get heat, and it is used in an electric cooker. Okay, then next application is, that is the next substance is tungsten. Okay, the bulbs that we are used in our home, there are, we see, very small wire of tungsten is used. Okay, due to the passing of electric current, okay, two terminals of bulbs are connected by this tungsten small wire. Okay, and as it also has very high resistance. Okay, due to the high resistance, what happen again, heat is produced and also light is produced there. Okay, what happen, due to the high resistance of a tungsten wire, heat and light also produce there. This tungsten has very high melting point, that is the 3400 degree Celsius. Okay, means up to which its temperature will increase, it will give us heat as well as light. Okay, so such a way that in the heating effect of electric current, what happen, if you connect any resistor in a circuit, then we have to do some work to pass charges through that resistor, and according to Joule's law, whatever the work we do there across that resistor, that will get converted directly into the heat or light. In some cases light, in some cases heat. Okay, so this effect is called as the heating effect of electric current. Heat is produced across resistor in an electric circuit due to the electric current. That is simply called as the heating effect of electric current. Electric cooker, electric bulb, electric water heater. Okay, so that are the some examples of the heating effect of electric current. In that appliances we get directly heat from the electric current. Okay, that is why light is required to use this electric appliances. Okay, so up to now you have to study the Joule's law of heating, that is H is equal to I square RT, this law. Okay, that is the energy transfer in an electric circuit. The next topic we are seeing, that is the heating effect of electric current, heat produced in an electric circuit due to the passing of electric current. That is the heating effect. Okay, so remaining part of this chapter we will see in next lecture. You read that much covered part. Okay, because problem also asking that, and this some small questions also asked on these topics. Okay, so that read carefully, and if you have any doubts then ask in comment of this video. Okay.